Hi everyone, I'm Sameer Mohata and I am a graduate student in construction management program at University of Florida. Our paper presents requirements of bridge inspectors gathered to serve as guidelines for designing a safe, cost-effective, automated bridge inspection system. Let me introduce the authors. Dr. Eva Agapaki is Director of Digital Twins Lab and AI expert at University of Florida, and our community collaborator, Mr. Felix Padilla, who is working senior bridge inspector in Florida Department of Transportation. Even though the study is carried out in Florida, many developed countries are facing the problem of aging infrastructure and their maintenance. We will go through the maintenance practices that are currently implemented, what state of research is, and the research gap this paper aims to address. Let me first introduce what bridge inspection is and why transportation authorities spend huge sums each year to conduct inspections, along with some data on bridges in US and specifically in state of Florida, where our research is focused on. Following the collapse of Silver Bridge in West Virginia in 1968, the National Bridge Inspection Standard was established to locate and evaluate existing bridge deficiencies to ensure safety of the moving traffic. There are more than 600,000 bridges in USA, and 42% of them are at least 50 years old, meaning they are in their end of life phase. Our 46,000 bridges are in poor condition with an estimated repair cost of $125 billion as compared to $26.5 billion of dollars of funding under recent infrastructure investment. A bridge in poor condition doesn't necessarily mean that there is an immediate danger of collapse. Out of the 46,000 poor condition bridges, some are only restricted to light vehicles, some get occasionally flooded, some were simply built to standards that are not acceptable today. However, the only way for them to continue serving their purpose is if they are properly maintained by virtue of detailed inspection. Federal Highway Association requires that every bridge must be inspected every 2 years. However, to do visual inspection, inspectors need access which can require traffic closure, long detours, and can be unsafe. It is estimated that Florida drivers waste 18 hours or $1,000 each year in traffic congestions. Now let's look at the bridge inspection process. First, bridges are visually inspected and significant defects like cracks, corrosion, or section losses are measured and tested. Findings on the condition of components are documented by bridge inspectors in an inspection report. Inspectors, based on their training and experience, assign structural elements a condition rating, and then that report is updated in bridge management system for engineers to review and give out work orders for maintenance. After reviewing the current inspection practices and state-of-the-art research for all steps of bridge inspection, we found out that existing systems only automate parts of the complex bridge inspection process without necessarily addressing the needs of bridge inspectors. To address this gap, we first wanted to understand what inspectors' workflows are and when performing the inspection, and how computer vision and AI can facilitate most critical inspection process. Roughly, an inspection can cost around $10,000 and whole process can take up to 90 days. As the condition of structure worsens, the efforts required for inspection will increase. We conducted survey and interview with bridge inspectors, state maintenance engineers, private reviewers in state of Florida to derive software and hardware requirements for an automated inspection system. The development of an automated system is part of our future work. Before an inspection, bridge records such as images of old defects, guidelines to define severity, and plans are required. The condition rating given to a bridge is subjective depending on the training and experience of bridge inspector. Use of AI can eliminate this subjectivity. During the inspection process, we identified different activities that inspectors perform while reporting the bridge condition. The distribution of time spent on each activity shows that highest time is spent on field, followed by reporting. This clarifies the need of automation in both activities. Inspectors reported that they perform multiple inspections in a tour, which also includes high mast, light poles, and traffic management system. The graph shows the maximum number of inspections performed for each type of structure in a tour. The time elapsed from inspection to reporting varies from 2 to 7 weeks. Inspectors revealed that multiple inspections and the time elapsed can sometimes cause mental confusion, leading to difficulty in remembering relevant information. 70% of inspectors reported that some degree of automation is needed in the reporting process, which can keep track of observations in real time, eliminating the paper redundancy. Research has been done to detect and identify defects such as cracks, corrosion, and delamination. The graph shows prioritized list of defects in response to the questions asked to inspectors on using automated system with defects detection features. The survey also revealed that inspectors would like to have modern tools such as drones to narrow down areas of defects so that the entire bridge need not be inspected manually, thus limiting the need of traffic closure and heavy snooper trucks. 80% of the inspectors are inclined towards use of drones. However, skepticism comes from need to pilot the UAV. The predefined flight path, obstacle avoidance, and autonomy of flying drones can eliminate the need of extensive training for the equipment. It was also revealed that automation in determining bridge and roadway geometry, average daily traffic, along with size and location of defects can be very useful to derive accurate bridge condition. To detect and quantify defects, and in order to maintain relevance to the structure, a digital twin is highly recommended for maintenance. However, 78% of inspectors reported that digital twins are not available. Laser scanning and photogrammetry tools can be used to reflect as is condition of the bridge. We also ask bridge inspectors to decide which functional features will be useful in the automated system. The list shows features such as field measurement, image collection, and multi-visual collaboration are highly useful, along with 3D model generation and defect detection. With the finding from this study, a complete automated system combining data collection, data assessment, and condition rating prediction can be developed based on the needs of bridge inspectors with help of proposed guidelines. The vision of the project is to overcome substantial limitations of manual inspection and improve value of money in the maintenance of aging bridge stock. An automated system can provide transportation authorities with tools based on AI, accelerating data collection, 3D model generation, and report processing. A predictive maintenance program can be used to extend useful life of bridges, thereby minimizing the need to replace large number of bridges within short time. Thank you. I'll be happy to answer any questions you may have.